Lesson 7.3, multivariable linear systems and row operations. What we're going to essentially do in this lesson is create matrices from systems of equations and then use those matrices to solve the systems. To start this lesson, we're going to review some ideas from solving linear systems. So you don't have to write these down, we'll just refresh on them. So the following operations will produce an equivalent system of linear equations. The first one says we can interchange any two equations of the system. If we had two linear equations that we were solving, doesn't matter which one we put first or second, that's not going to change the outcome. Second one tells us we can multiply or divide one of the equations by any non-zero real number. We know that to be true from any linear equation we've worked with. As long as you multiply or divide by the same value to both sides of the equation, you're going to be okay. And then the third one, we can add a multiple of one equation to any other equation in the system. And that's an idea we used when using the linear combinations or elimination method to solve systems of linear equations. So these ideas are just a review of things we talked about when solving linear systems. We're going to use those same ideas later when solving systems using matrices. Now we need to talk about the row echelon form of a matrix. A matrix is in row echelon form if the following conditions are satisfied. First one, rows consisting entirely of zeros, if there are any, occur at the bottom of the matrix. The second one, the first entry in any row with non-zero entries is 1. And the third one, the column subscript of the leading 1 entries increases as a row subscript increases. That third one's going to be kind of confusing, I'm sure. So we're going to go through an example next, and I think that is going to make more sense on what that third condition is referring to. So now we're going to look at a couple of matrices. One of these matrices is in row echelon form, the other is not. So we're going to talk about some of those conditions that we just referred to on the previous slide. The one on the left is not going to be in row echelon form. Okay, the one on the right is. The reason the one on the left is not in row echelon form is because the second condition told us that any entry in a row where there are non-zero entries, the leading entry must be a 1. So if we look at our first non-zero entry in this row, it is a 2, so that condition is not met. Even if we go to the second row, our first non-zero entry in that row is going to be a 3. If this is in row echelon form, the first non-zero entry has to be a 1. So a couple conditions are not met. There's also that third condition which is not met, which tells us that as we go down one row, our first non-zero entry must be one column over. So from the first row to the second row, we're okay because our first non-zero entry is one column to the right. But now if we go from the second row to the third row, our first non-zero entry starts in our first column where it should start in the third column if it's going to be in row echelon form. Now let's take a look at the matrix at the right and determine why it is in row echelon form. If we look at the first entry, the first non-zero entry in each row, that value is a 1. We also have the third condition where that is met because if we go down one row, the first non-zero entry is at least one column to the right. So from row 1 to row 2, we're fine. And then if we go from row 2 to row 3, our first non-zero entry is one column to the right. So all those conditions are met. The matrix at the right is in row echelon form. Before we get into writing a matrix in row echelon form, we have to talk about the operations we can perform on a matrix to get it into that form. The first one is we can interchange any two rows in a matrix. The second one is we can multiply all elements of a row by some non-zero real number. And then the third one is we can add a multiple of one row to any other row. If you look at these three operations, they should seem very similar to the operations we performed on linear systems that we talked about in the beginning. So now we're going to go through the process of solving a system of equations by creating a matrix and writing that matrix in row echelon form. So the first thing we need to do is take this system and create the matrix, which you can see down below. All we have to do is take the coefficients and constants from each of the equations and place them in the matrix. So for the first equation, we had 2, 3, -1, -1. First row in our matrix, 2, 3, -1, -1. Second equation, -1, 5, 3, -10, -1, 5, 3, -10. Third equation, 3, -1, -6, 5, 3, -1, -6, 5. So we just take the coefficients and constants from our system, create a matrix from those values. Now we're going to take our matrix and go through those three operations we just discussed to get this matrix into row echelon form. Before I get started, I just want to say that there are many different ways you can write a matrix in row echelon form. There's not one correct way. The steps can be interchanged. So what I go through, you could have gone through a slightly different process to get it into row echelon form as well, and that's perfectly fine. So to start this out, I know that I want each of my rows to have the first entry be a 1. So looking at our rows, the second row has a first entry of -1, which is close to 1. So what I'm going to do is interchange rows 1 and 2. The notation we use to indicate the operation we're using, we have an R indicating a row operation, and then our subscript is a 1 and a 2. This just means we're interchanging rows 1 and 2. So now we get the matrix -1, 5, 3, -10, 2, 3, -1, -1, then 3, -1, -6, 5. Now for row 1, I need to make this coefficient 1, so we have to multiply this whole row by -1. The notation we use is pretty straightforward. We're just multiplying -1 times row 1 and replacing that. So now we have 1, -5, -3, and 10 for row 1. The next step in the process is to try to get this entry in row 2 to be 0, because the third condition for writing this in row echelon form was that as we go down a row, the first non-zero entry must be at least one column to the right. So we need to make this value 0. How we can do that is multiply the first row by -2, because then if we take -2 plus 2, that's going to create a value of 0. So we're going to multiply row 1 by -2 and then add that to row 2. Notice the notation we use. We're taking -2 times row 1 and then adding that to row 2. When we go through this process, row 1 does not change. We're just multiplying that value times row 1 so that we can change row 2. So once we take -2 times row 1, add those values to row 2 and replace them, we get 0, 13, 5, -21 for the values in row 2. The next step in the process is to make this value 1. So if this is 13, the way we multiply, or what we have to multiply that by to get it to be 1, is the reciprocal. So 13 over 1, we have to multiply by 1 over 13 to row 2. Now in row 2, we have 0, 1, 5 thirteenths, and -21 over 13. So you can see we're slowly getting closer to getting this in row echelon form. The only thing we have to work with now is row 3 to convert that so that these first two entries are zeros and the third entry is a 1. So next thing I'm going to do is multiply row 1 by -3 and add that to row 3 to replace it. That'll make this first entry 0. Remember that when we multiply row 1 by this value of -3, row 1 is not going to change. We're just multiplying row 1 by -3 so that we can add it to row 3 and replace row 3. Once we perform that operation, row 3 now becomes 0, 14, 3, -25. Now we have to make the second entry a value of 0 as well. So we're going to multiply row 2 by -14 and add it to row 3. After we multiply -14 by row 2 and add it to row 3, now we get row 3 to be 0, 0, -31 over 13, -31 over 13. If you're not sure where these values came from, you just have to go multiply 5 over 13 by -14 and add it to 3, getting a common denominator. That simplifies down to -31 over 13. If you take -21 over 13, multiply that by -14 and add it to -25, that simplifies down to -31 over 13 as well. So last step, we're very close to being done. Last step we have to do to make this entry a 1 is to multiply it by the reciprocal. The reciprocal will be negative 13 over 31. Once we do that, now we get 0, 0, 1, 1 as our entries in row 3. Now we can see that our matrix is in row echelon form. The first non-zero entry in each row is 1, and as we move down a row, our first non-zero entry moves over at least one column. So that was a process of writing it in row echelon form. Now we're going to go through how this is useful, helpful to us when we're trying to solve the system of equations. So let's refresh what we started with and where we're at right now. We started with this system of equations, and we wanted to solve this system, so we want to solve for the values of x, y, and z. We're going to use the process of writing this system of equations in matrix form. So far, we've written that in row echelon form. Now I'm going to show you why having it in this form is useful. So first, when we wrote this in matrix form, these are the coefficients in front of our x terms. These are the coefficients in front of our y terms. These were the coefficients in front of our z terms, and then these were the constants by themselves. Now we're going to use those same ideas, except use the matrix that is in row echelon form. So using our row echelon form of the matrix, now we can rewrite our system of equations. We would have x minus 5y minus 3z equals 10, y plus 5/13 z equals negative 21 over 13, and z equals negative 1. So if we're trying to solve for the values of x, y, and z, we already know what our value of z is. In our second equation, we just have two unknown values, but now we know the value of z, so we can plug that value of z in, and that will allow us to solve for the value of y. Then if we go to our third equation, now we know what z is, we know what y is, we plug those in, we have the ability to solve for x. So first, let's plug 1 into the second equation to solve for the value of y. Now we have y plus 5 over 13 times 1 equals negative 21 over 13. To get y by itself, we would subtract this value to the other side. Negative 21 over 13 minus 5 over 13 is negative 26 over 13, which simplifies down to not 2, but negative 2. Now that we know the value of z is 1 and the value of y is negative 2, we need to plug those values into the first equation so that we can find this value of x. After plugging those values in and simplifying for x, we get the value of x to be 3. So the solution to this system is the ordered triple 3, negative 2, 1. Make sure to list the terms in the correct order. We always go x, y, then z. We're briefly going to talk about reduced row echelon form, which is essentially row echelon form on steroids. We continue with our row echelon form, those row operations, until we get it a matrix in which every column that has a leading 1 has zeros elsewhere. So if we look at an example, we would get it so that we have this row echelon form such that the first entry, the first non-zero entry in each row is a 1, and every other entry below that or above it, every other entry in that column is a 0. We have our first non-zero entry in this row is a 1. Every other value in that column is 0. The same thing here. Okay, so now we could quickly see that x would be equal to 4, y would be equal to 3, and z would be equal to 7. The last thing to discuss in this lesson is an invertible square linear system. So the main thing you need to get from this slide is that if we have three different matrices being multiplied, we have matrix A, we have matrix X, which consists of our variables, and then that is equal to matrix B. If we want to isolate, get matrix X by itself because that contains our variables, then we're essentially doing the operation that you see down below. X is going to be equal to the inverse of matrix A times matrix B, as long as the inverse of matrix A exists. And the order in which you multiply these two matrices is important. you cannot take B times the inverse of matrix A. You have to make sure that inverse comes before matrix B. This is relating to what we talked about earlier, that the commutative property for multiplication does not hold true for matrices. So make sure you do not multiply them in that form. In this example, we're going to use inverse matrices to solve this system. We have 2x minus 3y equals 0 and 2x minus 2y equals 10. You can see how we're going to create those matrices that you saw on the last slide, matrix A, matrix X, and matrix B. So the coefficients from our variables, this is called our coefficient matrix, is going to be matrix A. So we have 2, negative 3, 2, negative 3, 2, negative 2, 2, negative 2. Our variable matrix, which is matrix X, is going to consist of our variables. We have our variable X and our variable Y. This can tend to get confusing. We have a matrix that we refer to as X. We also have a variable X within that matrix, so don't get confused by that. And then matrix B is going to consist of our constants. So we have 0 and 10, 0 and 10. So now we're going to use that formula to set up this matrix equation. So we have our matrix A times our matrix X, and that is equal to matrix B. If we want to get matrix X by itself, we have to find the inverse of matrix A if it exists, and then we're going to multiply that by matrix B. So to find the inverse of matrix A, we're taking 1 over the determinant. This inverse exists as long as the determinant is not 0. So we took 2 times negative 2, which is 4, minus negative 3 times 2, which was negative 6. So if we have negative 4 minus a negative 6, that simplifies down to 2. We interchange the elements or entries on our main diagonal, so that's why we have a negative 2 and a 2. And then we negate the entries on the other diagonal, which is why we get negative 2 and positive 3. Multiply that scalar through. The inverse of matrix A is negative 1, 3 halves, negative 1, 1. Now we have to multiply this inverse matrix by matrix B. Now we have matrix X isolated by itself. We have our inverse matrix times matrix B. So we have a 2 by 2 multiplied by a 2 by 1, which means the product is going to be a 2 by 1 matrix. Using matrix multiplication, negative 1 times 0 is 0. 3 halves times 10 gives us 15. 1 times 0 is 0. 1 times 10 gives us 10. So that means the solution to this system is going to be the ordered pair 15, 10. Our X value is 15. Our Y value is 10. To end this lesson, we're going to go through one more example of taking our system of equations, writing this as a matrix, and then getting it into row echelon form. What I recommend you do at this point is to pause the video, put this system into a matrix, and then try yourself to write it in row echelon form. After you tried, you've gone through, if you get all the way through, good for you. Then you can start the video. I'm quickly going to go through the steps to show how I simplified this to get it into row echelon form. Remember, you could have gone through different steps and still gotten to the same outcome in the end. So first, writing this matrix, or this system in matrix form, we have 1, negative 1, 2, negative 3, 2, 1, negative 1, 0, negative 1, 2, negative 3, 7. First thing I chose to do was multiply row 3 by 2, and then add that to row 2. Next, I added row 1 and row 3 together. After that, I interchanged rows 2 and 3. The next step, multiplied row 2 by negative 5 and added that result to row 3. And then the last step to get it into row echelon form was to multiply row 3 by negative 1/2. So here's the matrix I ended up with. You could have taken different steps to get this into row echelon form. And even if you have it in row echelon form, you might have some slightly different numbers compared to what I have. And that's okay. The only way to tell whether or not you went through correct steps and you didn't make a mistake is to take your row echelon form, convert that into a linear system. So mine turned out to be x minus y plus 2z equal to negative 3, and then y minus z equals 4, and then z equals 3. If I went through like we did earlier and solved this system, I get the order triple negative 2, 7, 3. So if you want to check to make sure if your reduced, or not reduced, but if your row echelon form is correct, you can solve the system, create the system, and solve it to see if you get the same result that I did.